that's right. We had a very similar question, I think, actually, to this, right? When we were back doing the notes. So this is be fairly simple. I have Q is equal to CV. I know that Q is equal to CV. C is constant for both of these. They're the same. But the one with the bigger voltage will have the bigger charge. And C2 has the bigger voltage, 10 volts. What must be done in order in a capacitor to increase the amount of charge it can hold for a given voltage? How can I increase the amount of charge it can hold? And we have these two geometric quantities, the area and the separation. Wonderful. I'll stop at 45, 45. 5 more seconds. Okay, that's right. D is the right answer. If you make those plates bigger, they can hold more charge, or if you move them closer together, they can hold more charge. Okay, a parallel plate capacitor has a voltage of 400 volts, and then it stays connected to the battery. If the plate spacing is doubled, what happens? Which of these? Either through the voltage or the charge. You keep it connected to this power supply, but you double the plate spacing. We're looking at two different expressions here. Stop at 110. 110. Let's see. So if I double the plate spacing, that means I increase this by a factor of 2. That's going to change my capacitance. It's going to lower it by a factor of 2. And so if I have half the capacitance, now which of these is going to remain constant? Q or V? V remains constant, right? Because it's on 400 volts. So if that remains constant, that means that I'm going to have half the charge. So C should be the right answer. That's right. Am I getting this okay? Yeah. Just want to look at the interplay in these two mathematical relationships, how they affect one another. All right, this one's a little bit different. Here you disconnect it from the battery, so the voltage is no longer staying constant. We had a similar question to this earlier. Stop at 110. 110. 10 more seconds. see. I'm going to go and mark B right after. I don't know what it is right off. I'm going to mark B correct. Let's see. So I know I have these two expressions. C is epsilon naught A over D. What am I changing? Doubling the plate spacing. Yeah, so I get half the capacitance. And then I go over here. I know Q is equal to CV. I'm having the capacitance. What's remaining constant? Right, so once I remove that power supply from the capacitor, it has a charge on it, and that's not going to change until you discharge it or add more charge to it. So this remains constant. So if I have half the capacitance, to keep Q constant, I have to increase that by a factor of 2. And so it was 400, so it has to be 800. Is that what I marked correct?
No, you
Okay, yeah, so it should be D. All right, now see that? How the charge has to remain constant here. And so if I decrease this, this has to increase in order to keep that same constant charge. You with me on this? I had questions like this on previous tests, so, you know, likely see stuff like this again in a couple of weeks. Let's see, we haven't done this yet, so we'll come back to this. Alright, let's see. So I think we left off with capacitors in parallel. Have we done capacitors in series yet? No. Is that next? That's next. Oh, we have an example here we're going to do. So here I have these two capacitors. Have we done this one? No. All right, this one's pretty simple, all right? And actually on your test, you know, you're going to have more complicated circuits than this. But we're sort of building up to those. So let's just look at this one. I want to know what is the charge on C1 and C2. Now we had some rules about capacitors in parallel. Do you remember what they were? All right, yeah, so they have the same voltage. What was the second rule about the equivalent capacitance? How do you find the equivalent of capacitors in parallel? Are we going to do equivalent capacitance? Yes, we did, didn't we? Right, see, the equivalent capacitance is just the sum. C1 plus C2 plus however many capacitors there are. And then the third is that just definition Q is equal to CV. So those are our three rules for capacitors in parallel. As I said, we'll have similar rules for capacitors in series, but those are sort of our governing principles. So here, I know that they have the same voltage, so I have 10 volts here and 10 volts here. And then I can find the charge fairly simply, just by C times V. So what is the charge on C1? The charge on this capacitor. It's going to be 10, right? So it's C1 times V1, which is 1 microfarad times 10 volts, which is 10 microcoulombs. And then this one similarly is C2 V2, which is going to be 20 microcoulombs. So the voltage on each capacitor is the same. That is, it's 10 volts for each of these. Okay. Oh, no, we hadn't gotten to the equivalent capacitance yet, had we? I'm sorry, it's right here. Yeah, so this is called the equivalent capacitance. How did you know, Jose?
I just went back and looked at the formula sheet.
Oh, the formula sheet. There you go. So, yeah, I'm sorry.
Why, you thought it was some kind of magic?
You should have owned it, yes, that you just knew.
No.
That you intuited it.
There's no lie of that.
All right. So if I have two or more capacitors, I can replace them with what we call an equivalent capacitor. You haven't done resistors in series and parallel yet, have you, in lab? You just did Ohm's law? Yeah, okay. So your next lab, you'll deal a lot with equivalent resistance, and we'll deal with capacitance in a similar way, where I can take a lot of capacitors and condense them down into one equivalent capacitor. It's fairly useful for being able to simplify circuits and find out exactly what's going on in circuits, as we'll see. So if I replace two or more capacitors, this is called the equivalent capacitance, or the equivalent capacitor. I'll abbreviate it as CEQ, the equivalent capacitance. And for capacitors in parallel, I just add them up. Are you going from here? I'll give you a second. All right, so the equivalent capacitance is just C1 plus C2 plus C3 plus dot, dot, dot. So if you have 100 capacitors in parallel, then you just add up all 100 capacitors. So for example here, I have two capacitors, 1 and 2 microfarads, so the equivalent is going to be 1 plus 2 equals 3 microfarads. All right, that's simple enough, right? All right. Let's try this quick test. Here I have this circuit. I want to know what is the charge on the 3 millifarad capacitor. What is the charge on that 3 millifarad capacitor? And then I'm going to ask a second question. I want to know what is the equivalent. Don't click this in yet, but go ahead and answer the first one, and then I'll stop it and restart it. What is the equivalent of this circuit? Is it still answering the first question, please? I'll stop at 105 for that first question. Okay, that's right. So simply put, I know that the voltage up here is 18 volts because of that first rule. Capacitors in parallel have the same, what is it they have? The same voltage, right? And so Q is equal to CV. So that's 3 millifarads times 18, which is 54. Now what is the equivalent capacitance of this circuit? I have there's 3, 6, 12, and 24 in parallel. All right, I'll stop at 25. Excellent. You just add them up, so it's 45 microfarads. What's that? All right. Yeah, these are pretty simple, okay, but we're really shooting towards combination circuits where we have capacitors in series and parallel in the same circuit, and they'll be more complicated, more challenging for you. So, all right, now with capacitors in series, we're going to have a similar set of rules like we did with capacitors in parallel. Let's see if we can remember all the rules. Capacitors in parallel have the same what? Voltage. To find the equivalent, you do what? You just add them up. And the Q is equal to CV. So those are our three rules for capacitors in parallel. In series, we'll actually add a fourth rule. All right, but the first rule for capacitors in series, remember capacitors in parallel have the same voltage, but capacitors in series have the same charge. Not the same voltage, but the same charge. All right, so this comes about, when you have capacitors, you don't have a flow of what we call current. There are no charges actually passing through the devices. If there are charges passing through, then you get what of the capacitor? What happens to it? It blows up, right? It burns up. Charges go through that paper, and that causes it to catch on fire, and it's not good. Like, that's not the intention of a capacitor. But instead, what you do get is you get an induced charge. Induced charge I get charges on this plate that are positive. That's just because it's hooked up to the positive terminal of this battery. And because I have those positive charges there, I get negative charges on this plate. So if I have 3 positive charges on the positive plate, then I get 3 negative charges on the negative plate. And that leaves a deficit of electrons over here, so that I get 3 charges on the negative plate there. And then similarly, I get 3 negative charges. Goodness, bless you. All right, so because of this, that they're really just setting up an induced charge within the capacitors, they all have the same charge. You with me on this? Like on an induced charge, remember we had like the metal rod, if you had a certain positive charge on one end, then you had the same negative charge on the other end, because I'm taking away from one end to make the other end induced. All right, so they have the same charge. And then the equivalent capacitance for capacitors in series is a little more complicated. It's 1 over C1 plus 1 over C2 plus the inverse of however many capacitors you have. You might see this written elsewhere like this. It might even be written on your equation sheet like this. I'm not sure. This is the same expression. 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over... Yeah, that's the last time you can sneeze. All right. No, I'm joking. All right, so that is those are both the same expressions. Y'all see how those are the same? Just taking the inverse on one side. How is it written on the equation sheet? Somebody tell me? I think the left-hand side.
Just like you did the last
The last one? Okay. I think that's probably more common, like in other books and what have you. All right, but this is, when you're finding the equivalent, this is the work that you'll do. So, for example, y'all try this one out. Tell me what you think the equivalent capacitance is. Let's do a clicker question actually on it. A, B, C. Is it 9, 2, or 1/2 microfarads? Which is it? The equivalent of this 3 and 6 microfarad capacitor. About 10 more seconds. Stop at 50. You'll find that on the test, like in the multiple choice and even in the free response, that I use numbers that are really simple. So, and you'll begin to recognize some of those number patterns. A 3 and a 6 are one of those. I'm going to go ahead and pull it away, because it gives you a nice round number. B is the right answer. I just do 1 over 3 plus 1 over 6. That's going to be the same as 2 6 plus 1 6, which is 1 over 3 6, or 1 over 1/2, which is equal to 2. All right, so B is the right answer. Let's try another one. Now, this isn't really a rule, but the charge that's found on C is the charge is the same on capacitors in series. That was our rule number 1. Caps in series have the same charge. All right, well, I'm going to have a rule 1A, like a subset of this rule, and that this charge is the same as the charge on the equivalent capacitor. So if I have 2 capacitors, they have the same charge, and that charge is the same as the charge on the equivalent of those 2 capacitors. All right, so we'll see this here. out of this circuit, I want to know the potential difference across C1 and C2. Now the first thing I want to do is find the equivalent capacitance. All right, so that's going to be 1 over 2 plus 1 over 4, and that's 4/3 microfarads. All right, 2/4 plus 1/4 is 3/4, and then the inverse of that is 4/3. All right. So if I redraw the equivalent circuit, I'm going to have a 4/3 microfarad capacitor there. Now, I can find the equivalent charge. Now, since the capacitors in series, they have the same charge. And so the equivalent charge is going to equal to the equivalent capacitance times the voltage. So when I say equivalent charge, what I mean is the charge on the equivalent capacitor. Let me write that here. All right, and so that was equal to, let's see, what was our equivalent? It was 4/3, right? Microfarads times the voltage, which was 8 volts. So this is equal to 32/3. I'm going to keep it in fractional form. These are fairly simple fractions. But on the test, you can do it in decimal form. It doesn't really matter to me. All right. So now I know Q1 and Q2. So this is equal to Q1. It's also equal to Q2 because capacitors in series, as we all know, have the same what? They all have the same charge. For capacitors in series, they have the same charge. So now we know two things about each capacitor. We know its capacitance and its charge, so we can find its voltage. V is equal to Q over C. Remember, this comes from our definition Q is equal to CV, so I'm just solving that for V. That's going to be Q1 over C1, which is going to be 32/3 divided by C1, which was 2, I think, right? And this is going to be Q2 over C2, which is 32/3 over 4. This is in microcoulombs, microfarads. Notice the micros cancel out and just leave me with volts. That's 16/3 and 8/3. What is the sum of those two numbers? 8. Right, so 16/3 plus 8/3 equals 8. Does that ring familiar to you in any way? 8 volts? Right, so that's going to be our... How many rules have we had now? This is our fourth rule. For our fourth rule, when electrical devices are in series, I'll write it down here, the sum of their potentials is equal to the total of the source of the potential. The sum of their potentials is equal to the total of their source potential. In this case, it was a battery. All right, but we'll see in more complicated circuits that we'll take like an individual branch of a circuit, and we'll say the potential across this branch is X volts. And the sum of the potentials across each individual capacitor in series will equal that total. All right, also note here that C1, which had half the capacitance of C2, has twice the voltage. Or twice the potential. and this comes about from Q is equal to CV. I have this inverse relationship between C and V. So if C goes down as it does for C1 in comparison to C2, then V goes up. And this goes back because since capacitors in series have the same charge, that Q remains constant. That's a handy little rule that might help you when you're dealing with more complicated circuits, that the smaller capacitor has the larger voltage for caps in series. Okay. Well, let me rewrite this. So V is V1 plus V2 plus V3 plus however many capacitors in series I have. And so for example here we had 8 volts, which is the same as 16/3 volts, which was V1, plus 8/3 volts. That's equal to 8. 24 over 3 is equal to 8. All right? So let's try this quick test. So these are a little more complicated than the parallel circuits. In this one, you're going to have to find the equivalent capacitance first. And then find the charge on each capacitor, and then find the voltage on the 24 microfarad capacitor. All right, let's see. Stop at 310. 310. I'm going to ask you a couple more questions, a couple simple questions. Right, if you were going to rule the world, how would you do it? You would answer C, which is correct. All right, so here, first one, I find my equivalent capacitance. I do this 1 over 3 plus 1 over 6 plus 1 over 12 plus 1 over 24. And I find that that equivalent capacitance, I found it to be 24 over 15. All right, well, I guess that simplifies. 8 over 5. 8 over 5 microfarads. And then I can find my equivalent charge, which is going to be C equivalent times V, which which is 8 over 5 times my voltage, which is 18. And then that's going to be 144. Is that right? Yeah, 144 over 5. Or whatever your decimal is. That's in microcoulombs. So that means that I have 144 microcoulombs on that charge. And so if I want to know the potential, I'll just say V is Q over C, which is 144 over 5 divided by 24 microcoulombs. Farads. Oh wait, I'm sorry, I got this switched. There's microcoulombs up here, microfarads there, and then I get a voltage of 1.2 volts. All right. What do you think would be the voltage? Don't try to calculate. What do you think would be the voltage across this capacitor, which has half the capacitance? 2.4. Right. What about this one? Let's write that down back. 2.4, 1.2. What about the 6? 4.8. And the 3? 9.6. Now let's just do a double check. You know, there are lots of little checks that you can do. And one of the checks that I can do is that I can add all of these up. So that's 0, area 2, 11, 15, plus 3 is 18.0 volts. And notice that the sum of all those potentials equals that potential. So those are nice little tricks when you're dealing with very complex circuits. But you don't have to do the math, you can just look at them and say, well, the voltage here has to be twice the voltage there, or has to be half the voltage there, or whatever. Let's try a couple more simple questions. Let's say I have a circuit that looks like this. This is 12 volts, and these are all 2 microfarad capacitors. I want to know what is the voltage on that capacitor. Is it a 6, 4, 8, or 12 volts? Which is it? On that third 2 microfarad capacitor, which is it? 6, 4, 8, or 12 volts? You shouldn't really need to do any calculations with this. You should be able to look at it and say, yeah, I know what the voltage is on that capacitor. Think about how those capacitors are in relation to one another. All right, just a few more seconds. I'll stop at 1:15. I mean, you can do it the long way, but it's a lot easier just to look at it. Excellent. That's right. Right, they're all identical, so they all have the same voltage. It has to add up to equal 12. So I know then that I have 4 volts on each. Let's try this one. Try to do it without your calculator and see if you can get it right. I have 2 capacitors, a 3 microfarad and a 6 microfarad, hooked up to a 12 volt battery. And I want to know what what the voltage is. Is it 8, 4, 6, or 12 volts on the 3 microfarad capacitor? So I want to know the voltage on that capacitor. Which is it? 8, 4, 6, or 12? All right, I'll stop at, let's do 45. Oh goodness, all right. So remember, we said that Q is equal to CV, right? I know that for these, what is constant? These two capacitors, they're in series, and what do they have the same of? Right, so the charge is identical for both of them. So that remains constant. And I'm asking you, what is the voltage on the smaller of the two? So the one with the smaller capacitance, I want to know what its voltage is. Did I say charge? What is the voltage on that capacitor? And I also know they're separated by a factor of 2, so they have a factor of 2 difference in their voltages, and that the sum of those voltages has to add up equal 12. Let's try it again, okay? So first, is the 3 microfarad capacitor going to have a larger or a smaller voltage than the 6 microfarad? It's going to have a larger voltage because it has a smaller capacitance. So since they have constant charge, it has a larger voltage. Okay. Let's stop at 33. What was that? Oh yeah, A is right. Okay, so those are some nifty little rules that'll help you in sort of untangling these things. So if I have 8 volts here, that means I have what on the 6 microfarad? I have 4 volts, because 8 plus 4 equals 12. Those are kind of fun, right? Listen, I'm reading this book. I don't know if y'all care, but it's kind of interesting. It's about how people learn and what have you. And the guy says, like people do stuff like this all the time. Like they do, where you have a grid of 1 by 9, and you're trying to fill in numbers 1 through 9 in each little grid. Y'all know what that's called? A Sudoku, right? And people pay a lot of money to play Sudoku, and they spend many, many hours playing Sudoku. But the guy says that, a similar thing is if I have a right triangle showing that the midpoint from that right triangle is equidistant from all the vertices of the triangle. But that's also a puzzle, but people don't really like to do puzzles like that, right? But it's a similar puzzle to Sudoku. So I think these circuits are like Sudoku because you really just have a few simple rules, and then it's just a matter of sort of playing with the numbers to get them to work out.
If you want to play a mean puzzle, all you use a checkerboard and a lot of checker pieces. You take the checkerboard and in the 3 bottom corners, you put one in each part, and it's called getting out of prison. So to get out, you have to split each person into individual things. So if you had the one that's on the bottom part that's right here, the little L right here, not a full L, just a little corner, you'd split him into 2 to get those 2 out, and then the one that's in the middle disappears.
Okay.
I'd have to show it easier. Yeah. I can't explain for crap.
All right. So anyway, we digress. But I digress first. So, I'm just in chapter 1, so they haven't said how to make the right triangle as interesting as Sudoku yet. All right. Let's look at combination circuits. We still have a few minutes. So usually when we're dealing with circuits, they're not just going to be simple series and parallel circuits. They're going to be more complicated. So we're going to work through some circuits here. As I go through, we want to find the equivalent capacitance of this circuit. As I go through, each time I find a new component, I'm going to redraw the entire circuit. Now, it might come to be, like on the test, when you have not terribly difficult circuits that you don't need to do that, but I find that it's good for practice. So I would just do this each time, just redraw the circuit. Now, when you're finding the equivalent capacitance of a circuit like this, you want to start with the smallest component that is either only parallel or only series. All right, so notice we have several components within this circuit that are a combination of series and parallel. But what is a part of the circuit that is only parallel or only series? Huh? Okay, the 1 microfarad is in series with a much larger portion, that big branch up at the top. Alright, so I can't really do anything with it just yet. Limping?
Question.
Which ones?
Question. Is
The ones on top, right, yeah.
is 3 in series and parallel?
3 is in parallel.
In series?
This capacitor is in parallel with these and these.
But it's not in series with the 10 and neither 1 microfarad?
This whole thing is in series with the 1 microfarad.
So you can start with one circuit first.
Which one?
You can start with that and then choose the one separate.
Right. If I understood what you're saying
So
correctly.
you parallel is maybe equal to. You have something called parallel first and then go to the series.
No, the first thing that you do, that Limping said is, anybody else catch it? What is it that we do first? The top, right. Look, these two are in series. It's a simple series circuit. If I pick a point and go through them, I find no breaks in there. But I have more than one capacitor, so I want to simplify that. And so when I have capacitors in series, I do 1 over 1 over 2 plus 1 over 2, and that's equal to 1 microfarad. Alright, so my circuit now will look like this. I'll have my 1 microfarad in series with 3 capacitors that are in parallel. This is going to be a 1, 3, and a 7. Now what do I do next? Right. I'm going to take this branch and simplify it. And it's going to be 1 plus 3 plus 7, which is equal to 11 microfarads. And so my new circuit now will look like this. I'll have a 1 microfarad capacitor in series or parallel with an 11 microfarad. Right, in series. This is a 10-volt battery. Even though there's a bend here, like where I bend right here, there's not a break in the circuit. That should be obvious to you, but we'll see some circuits later where they're more out of like a grid-like fashion instead of being written like this, where it won't be so obvious. All right. There are no breaks in that circuit. And so now if I want to find the equivalent of that, I say 1 over 1 plus 1 over 11. I think I got 0.92. Is that what it is? 0.92? 0.92 microfarad. All right, so 0.92. So my equivalent capacitance on this is 0.92 microfarads. Okay. Now, let's say, can I go down from here? I'll give you a second. Let's say that I want to find the voltage across the 3 microfarad capacitor. So I want to find the voltage, the potential across this capacitor. Let me just lay out the steps for you first. Let me redraw it over here. So this is 0.92 microfarads. I can find the charge on this capacitor. That's really simple. Once I find that charge, that same charge will be on these 2 capacitors because they're in series. Once I find that charge, I can find the voltage on this capacitor because now I know its charge and its capacitance, so I can find its voltage. And once I find that voltage, how do I get the voltage on the 3 microfarad capacitor? No. Nope. They all have the same, they're in parallel, so they all have the same voltage. So whatever voltage I find here is the same voltage on all 3 of those. So those are the steps in cursive. Let's go through them. So I'm going to redraw that equivalent circuit right here. You can do it on this page, on the previous page, it doesn't matter. This was 0.92 microfarads, and this is 10 volts. And then I can find the charge on this circuit, which is C times V, which is going to be 9.2 microcoulombs. All right, so that's that charge. that charge is the same on these two capacitors. Remember, this was an 11 microfarad capacitor. It has a charge equal to 9.2 microcoulombs. So I can find the voltage, Q over C. This is going to be 9.2 divided by 11. 0.84 volts. All right, now, but remember, this capacitor was the equivalent of 3 capacitors in parallel. So if I redraw this again, this capacitor was the equivalent of these 3. If that capacitor, that 11 microfarad capacitor, has 0.84 volts, that means I have 0.84 volts here, 0.84 volts here, and 0.84 volts here. All right? So that's my answer. So the potential across the 3 microfarad capacitor is equal to 0.84 volts. Let me ask you another question. I'm going to go back to the previous page in just a second. Can I go back up? I'll give you a second. I want to know what is the voltage across the left 2 microfarad capacitor. I'll come back. Go back to this. So what is the voltage across this capacitor? Anybody? It's going to be, what is it going to be? What's the value? 0.42, right. So remember, this capacitor right here was actually 2 capacitors that were identical. Because they're identical, they're both going to have 0.42 volts. Those types of questions, you'll have a question like that on the test. Next time, we will work through an example. Let's try this quick test, though, this next quick test. We have a few more minutes, so let's... Just tell me, what is the equivalent capacitance of this circuit? I'm going to ask you another question in just a second. But what is the equivalent capacitance of that circuit? Which one are you going to start with first? The 2 2s, right. That's a nice simple, huh?
The series inside of a parallel inside of a series.
A series inside of a parallel inside of a series, that's right.
Sounds like some sort of evil mastermind. Like, this box, another box, and this box,
right.
Another box. In a minute, so.
Oh wait, I'm going to change this. I haven't given it to you yet. But I'm going to ask you, what is the voltage across this capacitor if I have a 12 volt battery down here? Right, but go ahead and do the equivalent capacitance. If you want to work on that second question, you can. The second question is, what is the voltage across this capacitor if I'm hooked up to a 12 volt battery like this? But right now we're doing the first question on the clickers. I'll stop at 215. 215. let's see, is that right? 1, that's right, A is correct. So you do these first, guys. That's 1 over 1 over 2 plus 1 over 2. That's equal to 1. Excuse me. And then I combine that 1 with my 3. Combine with a 4. If I combine these two, that's 1 plus 3, that's 4. 4 and 4. 1 over 1/4 plus 1/4. That's equal to 2. Now answer this other question. I'm going to start the clicker. What is the voltage across this capacitor? Try to do it just by looking at it. Try not to work through the numbers. It takes a long time to step through the numbers. But if you can intuit it, get a feel for the circuit, be the circuit, and you can figure out what the voltage is. This is our last question. About 10 or 15 more seconds. I'll stop at 135. C is correct. Next time we'll work through this, doing all the charges and stuff. Let me show you quickly. So if I have 12 volts, that means I have 6 volts here and here, right, because they're identical capacitors. That means that I have 6 volts across these because caps in parallel have the same voltage. And if I have 6 volts there, that means that I have 6 volts shared between these two capacitors. So I get 3 volts and 3 volts. We'll do some more like that next time on Friday. But y'all have a good day, okay? Test in just a couple weeks.